Hello and welcome back to Differential Equations, section 7.3, Matrices and Linear Systems. 5.3, that's what I meant. I did 7.3 in my pre-calculus class earlier, so, or 7.2 or something like that, whatever. So, matrices. What is a matrix? A matrix is simply a rectangular array of numbers. That's all it is. So, matrix rectangular array of numbers. An example would be A, B, C, D, E, F. This one has 2 rows and 3 columns. And we would call this matrix 2 by 3. So it's simply labeled that way. Now each entry has its location in space starting from the upper left corner. You can just have a single number. You can have a matrix, let's say 13. That's number 13 is still a matrix, except just we also know it as a number 13. You can have that. It's a 1 by 1 matrix with 1 entry, so not a big deal. We don't consider that too much. What we do consider is when we have multiple entries, and those multiple entries, the first entry would be 1, 1. It's a first row, first column. It's row and then column. So row 1, column 2, row 1, column 3, row 1, column 4, going on forever. These matrices can be as big as you need them to be. Think of Google. Google indexes all of the words and websites and everything into a huge billion by billion matrix or more. So if you want to work as a programmer there, you better know your stuff in terms of matrices and stuff. Otherwise, you will never be able to understand how the algorithms, search algorithms work in such insanely huge matrices. Now, we're moving to row 2, column 1, row 2, column 2, row 2, column 3, row 2, column 4, going on forever. Row 3, column 1, row 3, column 2, row 3, column 3, row 3, column 4, going on forever, and this is going on forever. So what you are getting here is the infinite matrix, but the way we label entries is this way. The important concept that we are going to consider a lot is the concept of a square matrix, because the square matrix is going to be covering what we had in a previous section. Even when you go to higher order derivatives, your matrices are going to be 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on. So, a square matrix number of rows equals number of columns. So number of rows equals number of columns. 2 by 2 matrix would be example. So for this one, I can just say A, B, C, D, and that's the matrix. So to add and subtract matrices, first they have to be the same size. So you cannot add a rectangular matrix 2 by, let's say 2 by 8 to a square matrix 3 by 3. That makes no sense. You have to have the same matrix, same size matrix, and then they will add. And the way you add is you add corresponding spots. So 1 1 spot to 1 1 spot, 2 1 spot to 2 1 spot, and so on. So to simply get this, so you have matrix A with entries A, I, J. So I stands for row, J stands for column, plus matrix B, or minus matrix B with this corresponding I and J's will give you the sum or the difference of A plus minus B IJ. So they have to have the same row and the same column. And you can also multiply matrix by a constant and just get the matrix where this constant distributes over every single entry that matrix has. So if you go 2 times matrix A, every entry in the matrix will be twice as large as the original matrix. And then we have the properties of these matrices, and you will see that even though matrices are full of numbers which obey a lot of properties that you guys are used to, matrix multiplication is not commutative. I have to be careful of that one. But a lot of other properties carry over. So, you should be used to this, should I say, loss of properties as you move on, because if you remember, limits are used to define both integrals and derivatives, right? Now, for limits, you have that multiplication of 2 limits is the limit of the product. But you don't have that for derivatives and integrals, right? For derivatives, you have product rule, and for integrals, you have either a u sub or the by parts, if you have multiplication. So you can do them separately. Now, for limits, you can. So now for numbers, you would say 3 times 5 is 15 and 5 times 3 is 15, but for matrices, it doesn't hold. So we have certain properties that work with matrices that you're used to having with numbers, and others would not. So what are the properties that work? Well, the property of, first of all, subtraction is understood as addition when you distribute -1 to the matrix B. So that's one of the properties. Now, we have a 0 matrix. So when you add the 0 matrix, or matrix to 0 matrix, you will get matrix back. Now, 0 matrix is defined as the matrix of all zeros, or how many you need, right? So that's what the 0 matrix is. We have commutative property for addition of matrices, and we have the associative property as well. And distributive property when the constant is involved, not another matrix. So we have C times A plus B is distributive property, so CA plus CB. And C plus D times matrix A is CA plus DA. So that's the distributive property. So these properties work with matrices. Now, very important creature is a column vector. So column vector would be A1, 1, A2, 1, A3, 1, A4, 1, going on forever. So it's a column vector. We call it a column vector, but it's actually a matrix. It's whatever amount of rows you have by 1, right? So this would be n by 1 matrix, but we call it a column vector. This creature is important because our x and a y, which are solutions, will be stuffed into the matrix like that. And you've seen it in a previous section. I wrote it a few times without explaining what it was. Now, matrix multiplication is a bit tricky. So matrix multiplication can be performed only in certain cases, right? In terms of numbers, we can always multiply, right? Just sometimes you use the calculator, sometimes you're not lazy and you do it by hand, right? But in general, we can always multiply numbers. You can't always multiply matrices. So what is the limitation? What is the requirement? Requirement is that the number of columns of the first matrix has to be the same as the number of rows of the second matrix. So, if I have two matrices, A and B, where matrix A is, let's say, I by J, and the second matrix is M by N, requirement is that J must be the same number as M. So that's the requirement. Number of columns of matrix J has to be the same as number of rows of M. And then you can multiply. Now, we multiply in this fashion. Matrix C is equal to matrix A times B, using the formula Cij, which are the components of the solution, is going to be the summation of k goes from 1 to p of Aik plus times Bkj. Now this is representation of matrix multiplication in terms of the summation, but it's much easier to understand this when you see the procedure and the way it works. So say you have a matrix A which is given as 2, 3, 7, 8, and you are multiplying that by a column vector 5 and what haven't used 4. There we go. Now, what you do is, so guys, remember this motion. So go like this and then go like that. So this and that. So I'm going to take 5, 4 and I'm going to put it on top of 2, 3. So 5, 4 goes on 2, 3. So 5 goes on 2 and 4 goes on 3.
Just like as if you would.
Yeah. You pick up the two values and then superimpose it. So what do we get? We get matrix multiplication works this way. You have 2 times 5 plus 3 times 4. And the bottom entry is 7 times 5 plus 8 times 4. Observe that your initial matrix was 2 by 2, and the second matrix is 2 by 1, and you're getting the answer 2 by 1. Now you just multiply this thing. 2 times 5 is 10 plus 12 is 22. And then 7 is 35 plus 32 is 67. So we multiply the two matrices by placing, so 5 will be multiplying the column 2 and 7, and 4 will be multiplying the column 3 and 8. and you just place them. All right, so let's do different example. How about we go, I don't know why I don't need to label anything. 3, 2, 4. So 3, 2, 4. And then 6, 5, and 1 times the square matrix 8, 7, 3, and 2, whatever. The input matrix has 3 rows and 2 columns. The other one is 2 by 2. So we see that the inner ones are the same, which was the requirement. The result must be 3 by 2 matrix. That's what the result is. So what I'm going to do is I'm going to take 8, 3 and put it over 3, 6. So I have 3 times 8 plus 6 times 3. And then I'm going to go 1 row down and have 2 times 8 plus 5 times 3. And then I'm going to go another row down and have 4 times 8, no coughing, plus 1 times 3. So these would be, when I use 8 and 3, the first column multiplied into 3 rows of the first matrix. And now I'm jumping and using 7, 2 on the first row. So I have 3 times 7 plus 6 times 2. And then I jump 1 down. 2 times 7 plus 5 times 2. And then I jump 1 down. 4 times 7 plus 1 times 2. You wish you took a red pill, huh? Oh no, the blue pill.
Wait. I already made a matrix joke before. Yeah, it was very hilarious. You totally missed that. It was pretty good.
Yes, Pandora. What I get 2 times 8. This one? It's this column. Sorry, this row and the column. So it goes. So you always have this motion. Pull, pull. Right? So this or right there, there, there. And then we move next one. But you move 1 over the result. When you rewatch this, it will be clear. You can see that you have 3 rows and you have 2 columns. Now all we need to do is to work out the numbers. So 24 plus 18 is 42, let's say. 16 plus 15 is 31. And 32 plus 3 is 34. No, 32 plus 3 is 35. And then I have 21 plus 12 is 33. And I have 14 and that's 24. And then I have something over here. That's a 28, 30, right? So there's the matrix multiplication. Now, for matrices, associative and distributive rules work, but commutative rule does not work. So your A, B, C is the same as AB times C, and your A, B plus C is the same as AB plus AC. So these two rules, here's the green check mark, work. Commutative rule does not work. Here, in blood, AB is not the same as BA. So be careful.
Could be.
There are exceptions to the rule. But if you can find just one case when it doesn't work, it's no mathematics just is not taking it. We also have something is called identity matrix. An identity matrix acts as number one. So what that means is that if you take a matrix A and you multiply it by I, which is the identity matrix, you will get A back. If you take I, multiply it by A, you will get A back. Now you would say, oh, you just did the commutative there. Yeah, I did, but this is the case where it works. In general, it doesn't work. So, tough luck. The I matrix looks like this. 1, 0, 0, 0, 0 going forever. 0, 1, 0, 0, 0 going forever. 0, 0, 1. So it has a diagonal filled with ones. It can be any size. 1 by 1 is just number 1. 2 by 2, 1, 0, 0, 1. And so on. So you can find the matrix in any. And we are finally getting to the place where we are defining an inverse. Because we need this. Inverse matrix. A to the minus 1. So first off, A times A to the minus 1 is going to give you an identity matrix I, which is really good because we have that function times the inverse of the function gives you x back, right? So, I mean, not times, composed. Gives you x back. So that should somehow translate, and it works. Now, the question is, how do we find, oh, actually, wait. So the inverse matrix, and we'll get the details later. And what else do I need? I need the determinant. And then we can calculate stuff. So the determinant, which is denoted as the absolute value of A, is going to be different for every matrix. There are formulas which you can calculate the determinant of the matrix. If you are dealing with 2 by 2 case, and that's generally what we are dealing with, so A, B, C, D, the determinant of that would be AD minus BC. Now, I need to call attention to notation, guys. You saw me earlier put the matrix in a square brackets, and over here you see me using non-square brackets like absolute value. That subtlety is actually notational difference between matrix is present or the instruction calculate the determinant. So when you see a matrix written within absolute values, you are expected to perform calculation, find the determinant. Okay? If you see, so let me make sure that you're getting it. So if I have 3, 4, 5, and 7 like this, this is just a matrix. Maybe it's defined as A or something, but it's just a matrix. And there's nothing you can do about it, just you can look at it, say it's pretty, and walk away, right? But if you see the same thing, 3, 4, 5, and 7, in absolute values, this means calculate the determinant, which means you will immediately go equal 3 times 7 minus 5 times 4. 3 times 7 is 21 minus 20, and determinant worked out to be 1. Bueno?
Does the determinant actually, like, what is that about?
So,
Do the same method in the multiplication.
so the determinant is going to be used to find the inverse. So it's a calculation. Yeah, it measures the matrix and gives it the dimensions and so on. So you can take linear algebra class for the Grigori detail or see me after class for the Grigori detail. So why are you asking me? It was one of those. Oh yeah, I passed the test, right?
Yeah, pretty much.
Oh, I see. So now I can finally write down the way to calculate the inverse, which is 1 over determinant of A times D negative B negative CA. So, if I want to compute the inverse of the matrix A given by 3, 4, 5, and 7, I will find the determinant. We already did. It's 1. And then I will swap the locations of 3 and 7. And I will put negatives on 4 and 5. And there it is. Now if I want to check, I will go 3, 4, 5, 7 times 7, negative 4, negative 5, 3, and I better get 1, 0, 0, 1 when I perform calculation, or we broke mathematics and then that's it. So I have 2 by 2 matrix and a 2 by 2 matrix, so the result will be 2 by 2 matrix. So 7 times 3 minus 5 times 4, and then 7 times 5 minus 7 times 5, and then negative 4 times 3 times 3 times 4, or plus 3 times 4, and negative 4 times 5 plus 3 times 7. So when you compute this, 21 minus 20 is 1, 12 minus 12 is 0, 35 minus 35 is 0, and again 21 minus, right? And this is the proof that the matrix you obtain is an inverse of your input matrix A, because in there, when you multiply them to check, you got the identity I. That's the way you check if the function is the inverse function, right? You do the function composition, and if it cancels down to x, it's an inverse. For matrices, if you do the multiplication between your original matrix and the inverse matrix, you have to come up with identity. If you're multiplying 3 by 3, right? Now, there are so many subtleties in linear algebra class talking about the square matrix is the matrix that would have the inverse. You're not going to find an inverse for a rectangular 3 by 7 matrix and so on. There are a lot of things that you can do with that. And now, what I want to do is I want to make these matrices work for us for differential equations. So when you take linear algebra, you play with numbers, right? But in differential equations, we are just using what we know, which means that I'm going to replace the numbers in these matrices with functions. Yeah. So we are going to see, say, x of t given as t squared e to the negative t. And a matrix A of t again, matrix of functions, is sine t 1, and then t, and then cosine t. So now I have a matrix column vector, which is 3 by 1 matrix, x given as t, right? And so what are we going to do with this? Yeah, we're going to stare at it. Oh, this is just introducing that if you take the derivative in respect to t, you will get x prime of t, which is just the derivative of it independent. So 1, 2t minus t to the negative t. So that's that. And if you take the derivative of matrix A, d dt, you will just have a prime of t to be cosine t, 0, 1, and negative sine t. So this is just to tell you that if you are taking the derivatives of matrices, you will do that component-wise, right? In each location sits the function which you take the derivative of, and you don't have to worry about, unless you have the product rule within and stuff like that. So now, why is this cool? This is cool because our good old systems that we had can be transformed using matrices into, well, you can transform into matrix, that's what I want to say. So if you have your good old x prime is equal to 4x minus 3y, and y prime is equal to 6x minus 7y, you can...
Can you just take the coefficients?
Exactly. You can quickly say that your matrix column vector of x prime, y prime is equal to the coefficients 4, negative 3, 6, and negative 7 times the column vector xy. Now, I did have this previously, but I didn't talk about it, right? So now we are experiencing the form here, written in blood, dx. I'll put the vector notation because that's a column vector. So dx or dt is equal to matrix P times the column vector x. So we are now, we took the system and we wrote it as a matrix, and then we are just now working on a notation. Observe that this notation doesn't have limitation on size. So that notation over there, when you look at it, you don't know whether it's 2 equations, 5 equations, 100 equations. And that's the power of linear algebra. It gives us tools to, instead of working on the first order differential equation and then the second order differential equation and then third order, and you're learning the rules and grinding through the stuff every single time, the differential, this matrix form says any order works. You can have 5 by 5 system, and we can just make a 5 by 5 matrix with 2 column vectors, one of derivatives and one of the functions, and that's it. So now, going back to our problem before, how would you solve this problem, right? What would you do to solve this problem? And I'm just trying to see if this is in the same section or they... Ah, great, it's not here. Or it is here. Okay, just give me 1 second. Yeah, it's not in this section, so we'll have to, what I wanted to do, we'll have to hold off for now and just deal with what they, all right, one step at a time, I guess. So we know now how to transform a system. And now at this point in time, it doesn't matter how many equations you get. Each equation will represent one row in this matrix. And you can see that if you take this one and multiply it here, equaling it to this x prime, you get the first equation. So 4x minus 3y is equal to x prime, which is the first row. Again, xy on 6 and negative 7, 6x minus 7y, so we do multiplication, and then y prime on the left. Now, you can, the first skill, actually, wait, the general case of this equation, dx prime over dt is px prime plus some function of t, which is also a column vector. Oh, come on. We have sustained the damage over here. There we go. Why so late? Now, when you solve these guys, you are going to end up with the solutions, which are given to you. So solutions will look like x of t is equal to 3e to the 2t and 2e to the 2t, and y of t is equal to e to the negative 5t and 3e to the negative 5t. So this is how the solution look like, and you can actually plug this in to prove that these are the solutions. You will simply put x where it belongs, and then the derivatives where they belong. When you do matrix multiplication, everything is going to work just fine. So that's how the solutions, that's what the solutions look like. Now we also have the superposition rule. Yeah, t disappeared. So the principle of superposition allows us to add. So if I have the overall solution x of t, I can add as many of these. So c1 x1, which is a vector, plus c2 x2 as a vector, plus c3 x3 as a vector, plus, and I can add as many of these as I need to. And each one of these is a vector, actually, which contains multiple equations. So we can represent any order, second, third, fourth, sixth, and all of the solutions will have the same complexity. I mean, some are going to be more annoying to solve than others, but in terms of difficulty, it's the same difficulty. I have to distinguish between annoying and difficult. And the only thing that we need to review before you hit the eigenvalues is, well, there's Wronskian again, right? We can, work that out. Row operations. If you have calculator TI 83, 84, and so on, they do have the row reduced echelon form, which is row operations to reduce it if you need to. So that's another thing to think about. Maybe I should... Now, when you read the book, you will quickly realize that to go from one step to another, sometimes you have to do half-page calculations. The book really doesn't have every step spelled out. So if you get stuck with anything, talk to me. We'll figure it out. But definitely read through example 7, 8, 9, right, to make sure that you're getting this stuff. So, what is my... what happened? Why are you confused? Yeah, I should be collecting the phones at the beginning of every class. You said I'm confused, and now I'm switching back to go, okay, so are we going to talk about the superposition? Are we going to talk about inverses? Like, at what point you fell off the truck, and then... Yeah. This kid sent me a message.
You probably haven't touched a lot of flashbacks with
All right. So let's convert one of these puppies, see what they look like. I think we just lost one. All right. Someone left. Oh wait, the class ends in like 30 minutes, right? So we have time.
5.
Yeah, what are we gonna do? Go home?
Yes.
So observe this system. We are having a system of 3 equations. We have 3 unknown functions, and it's also non-homogeneous because you have this 9t, negative 9t plus 13 and stuff. So the first hurdle, which I found throughout the years teaching this, is to explain the new notation we are using here. You see, you have x1, x2, and x3. That's instead of writing x, y, z. Because when you get into linear algebra mode for differential equations or anything like that, you are no longer limited to work with first order or second order, right, derivative, or third. You are working in whatever amount of dimensions you want. So instead of labeling xy and then xyz and then xyzw if you have 4 equations, we'll just switch that notation to x1, x2, x3, and then whatever we need to use as the index is much easier than, because once you run out of 26 letters in the alphabet, you turn to Greek, you turn to, I don't know, Japanese, and so on, and it's... So to convert this system, I have the the column matrix of derivatives. So this is the column matrix of derivatives. And that's equal to, and now I have a matrix P. Now matrix P is the one that contains the coefficients of the ones that have the functions. So it's a 3, negative 2 and 0, negative 1, 3 and negative 2, and then 0, negative 1 and 3. So this is my x prime vector is equal to matrix P times matrix P times the vector x, which is x1, x2, x3, and then plus the f of t, which is the negative 9t plus 13, 7t minus 15, and 6t plus 7. Guys, we are still not solving these things. These are just notation and writing it down. Yeah.
That would be evil if that was not before.
So now, we are considering dx dt is equal to 3, negative 2, 0, negative 1, 3, negative 2, 0, negative 1, 3. There we go. Times x. Oh, you didn't get that? It's 3, negative 2, 0, negative 1, 3, negative 2, 0, negative 1, 3.
That's x of n, or just x?
It's x because,
Is it all x's or just x?
well, when I put the arrow above means it's a vector. So it's whatever amount of rows, and you know because this is 3 by 3, this is a 3, so it has to be a 3. And now, since we ran out of time, we'll continue next time with, I'll just stop here and I say need to solve. So we'll figure out the way to solve this next time, and then we can finally get into eigenvalues and real cool stuff. See you in 2 days, hopefully larger numbers.